Welcome back to the next Unit 1 video. As you can see in this video, we're going to look at sound. So just a quick overview, we're going to look at some key terms. Okay, we're going to see, sample, sampling rate, okay, also called sampling frequency. We're going to look at the sampling resolution, again, also called the bit depth. Going to see what channels are and also what the amplitude is. Right, then we're going to look at the quantization process and what's meant by quantization levels. Right, also quantization error. We're going to look at the sampling rate and the sampling resolution's effect on both the file size and quality of the audio. Then we'll look at calculating the file size of an audio clip, and finally just some extra. Technically, this is actually not included in the syllabus, however, maybe it's just interesting. So something called Nyquist theorem and also Fourier transforms. This one as well, it's going to have something interactive at the end as well. Okay, so just quickly then, some kind of basic physics. Well, sound is going to be transferred as pressure waves and detected by our eardrums. Of course, based on the vibrations. Right, each wave has a frequency and a varying amplitude, and of course, the frequency, that's going to be how many peaks and troughs it has per second, and of course, amplitude, this is going to be. I mean, if we think about the wave, I mean, for sound, basically, it's just going to be the volume. So the higher the amplitude, of course, the amplitude just means the volume. Right, so if we're talking about sound, of course, sound from the real world, okay, that's going to be analog. And analog, that means a varying continuous signal. And of course, when we say continuous, this means it can have any value. Right, in contrast, probably it's going to say here, computers can only understand, digital or binary data. Right, so sound has to be quantized, and, I mean, what quantized means, it just means rounded to a discrete level. So when we say discrete, I don't know, maybe we can store, 0.1 decibels, right? We can store, 0.2 decibels, right? 0.3. But if we have continuous, of course, continuous, that could be, I don't know, 0.274, 915, etc. So of course, this is going to be continuous, right? It's going to have an infinite precision. Whereas, I guess, because computers don't have infinite memory, then we just have to round it to a discrete level. Again, for example, 0.1, 0.2, 0.3, right, etc. So that's going to be what the quantization process is, right? Just rounding the analog data, right, to a discrete digital value. And of course, here we can see the different waveforms, right? So the analog signal, that's going to be nice and smooth. In contrast, the digital signal, we see, of course, it goes up in these steps. And these steps are going to be the different quantization levels. Alright, so I think, we said this, right? Each discrete step in the digital signal is called a quantization level. Right, we're then going to use an analog to digital converter, or ADC, and that's required to convert the analog signal to a digital signal. Of course, to go the other way, then we're going to use a DAC, right, or a digital to analog converter. And I suppose if you've done IG, you're probably familiar with that. If you've not done IG, I guess maybe this is going to be new content. Right, okay, then let's look at some key terms. So one is going to be a sample, and that's a measurement of the amplitude of the sound at a given instance. So if we say here, I guess, here's the pen. So if we're just taking, if we've got a sampling rate of 1, then in effect our samples, where is that pen gone? Okay, here we go. Right, then in that case, right, I guess we're going to have one sample here. We're going to have another sample here at 2 seconds. Right, I guess I'll sample at 3 seconds. This is not going to be exactly on the line. So here we're probably going to have to round up to this quantization level. Of course, at 4 seconds we're going to be rounding down to this quantization level. I guess 5 seconds, maybe that's going to be rounding up to this one. Of course, just so on. Right, then if we look at the sampling resolution or bit depth, and this is going to be the number of bits per sample. And as we'll see, if we increase the sampling resolution, again, also called bit depth, that's going to have two effects. One, it's going to increase the accuracy of the sound. However, that's going to come at the expense of making the file size bigger. And same with this, right? Same with the sampling rate or sampling frequency. This is going to be the number of samples per unit time, right? So e.g. per second. Now, here I said, if we're just using a sampling rate of 1, then we're literally just taking, 1 sample per second. Realistically, I think a typical sampling rate is 44.1 kilohertz. So of course, 44.1 kilohertz. That means 44,100. So of course, that's going to be the number of samples, or I suppose the number of measurements of the amplitude, right, each second. So as you can probably guess, if we increase the sampling rate, well, again, the accuracy is going to go up. However, again, of course, well, the file size is also going to increase. Right, so if we assume this graph represents 1 second, what would be the sampling rate and number of quantization levels be? Okay, so that's kind of annoying. Yeah, maybe I should have fixed this. It seems this one has told us already. Right, yeah, the animation is a bit broken. So the sampling rate, well, 18 hertz. Well, let's actually just see how we've said, or how we've calculated that. Of course, well, here we've just said this is 1 second because, well, yeah, we've said, right, assume the graph represents 1 second. So I guess this is just going to be counting, well, of course, yeah, 1, 2, 3, 4. And if we do all of that, well, there's going to be 18. Likewise, well, for the quantization levels, we're just going to do the same. Right, so, well, 1, 2, 3, 4. And I think if we do that, right, it's going to be 13. Right, so let's think then, how many bits would be required to represent 13 quantization levels? And this is similar to, let's say, when we had images, and well, of course, if we want to represent 13 different colors, right, again, it's going to be the same calculation. So you just want to think, well, yeah, what power of n, right, is going to give us, more than 13? And then I suppose, yeah, sorry. Right, I suppose in this case, well, of course, right, one of the powers of 2 is going to be 16. And if we think of that, what it's going to be 2 to the power of 4 is going to be 16. Yeah, therefore, if we're using 4 bits, well, then, of course, yeah, we can represent 16 different quantization levels. So what we're saying is, well, yeah, the bit rate, okay, or also called the sampling resolution, right, is therefore going to be 4. Because if we remember, well, the sampling resolution, the definition, well, it was just the number of bits used, right, to store each sample. Right, so if we assume this snapshot, okay, so I guess now we've actually changed it. Right, so here, if we assume the snapshot instead represents, well, 0.002 seconds. Right here, well, again, we say, right, there's 18 samples as mentioned, right, so in this case, what would be the sampling rate frequency, right, i.e. the number of samples per second, yeah, and also the correct units be. So this one, I mean, basically, it's just kind of basic calculations, right? If we think, well, of course, well, there's 18 samples, right? The amount of time is what, 0.02, and if you do that, right, well, it's going to come out as being 9,000. And then the unit here, well, that's going to be hertz, right? So we're saying, well, there's, yeah, of course, 9,000 samples, right, each second. Yeah, okay, and again, I guess, well, that's the definition, right? The amplitude is recorded 9,000 times per second, and we say that each sample uses 4 bits to represent it. So from that, yeah, so, okay, right, here is just the information again. Right, so hence from that information, right, can you then calculate the file size of a 3-minute audio recording? And again, you can think, well, like, yeah, okay, so I suppose even with, yeah, okay, even without seeing the formula written down, probably just kind of logically or intuitively, you can probably work out what this formula is going to be. So if we say, well, this is the number of samples per second, right, this is going to be the size of each sample, right, therefore, well, of course, we can just multiply those together. Right, this will give us the, okay, this will give us the size in bits, or yeah, well, I guess the number of bits for 1 second. Right, then, of course, well, to get 3 minutes, well, then, of course, we just want to go, well, multiply by 60 to get 1 minute, then, of course, multiply by 3 to get 3 minutes. Now, if we multiply all of those together, right, of course, that's going to be in bits. So I think for this one, probably a reasonable unit is probably going to be, well, let's say megabytes or mebibytes. So first, then, if we divide by 8, right, then, of course, if we want to get it in, what, megabytes, so megabytes, we're then going to go, what, 10 to the power of 6. If instead we want it in, well, mebibytes, well, that's going to be 2 to the power of 20. Or, of course, remember, you can also write that as, what, 1024 to the power of 2, right, 1024 squared. So if you do all of those calculations, well, I guess, right, in megabytes, you're going to get 0.81. Right, and in mebibytes, well, of course, yeah, use 1024, right, or equivalently 2 to the power of 20. And I guess you're going to get this. And again, here's just the full calculation, right, if you want to see it. Right, so this one we've actually mentioned, right, so see if you can remember. So what's going to happen to the audio quality and file size as the sampling resolution or bit depth is increased? So if we just think, well, of course, the sampling resolution, well, this is the number of bits used to sort each sample. Therefore, of course, well, if we increase that, well, I guess, yeah, the obvious one, the file size is going to increase. But also the audio quality is also going to increase. And that's because, well, like, okay, let's say if we're using a low sampling resolution, then, right, maybe this is, one quantization level, right, this is another quantization level, right, this is another, yeah, that's another. Whereas let's say instead we're using a high sampling resolution, well, then we're just going to have much more quantization levels. Right, of course, yeah, the quantization level is going to be much closer together. Therefore, the sound that we can actually represent, or okay, well, let's say the sound that we can digitally store, is going to more accurately represent the original analog signal. So yeah, okay, well, of course, here we just say both increase. And then if we think what's going to happen, right, if the sampling rate, okay, also called sampling frequency, increases. And again, right, in this case, well, they're both going to increase. And again, that's just going to be for the same reason. Like, obviously, well, the file size is increasing because, well, well, yeah, of course, we're just taking more samples each second. Right, yeah, just taking more measurements. And well, again, like the quality is going to increase because, well, rather than say, sampling it here and here and here, instead, we're of course sampling much more sampling much more frequently, right? Therefore, of course, yeah, we can, well, okay, let's say the measurements that we store are going to be sort of more accurate, right, compared to the original analog sound. And if you want to say that more formally, well, you want to say the quantization error is smaller. And yeah, again, like we said, right, these sample values can more accurately match the real analog signal. So just to see this in graphical form, and I think this should be quite clear, hopefully. Well, if we start with the first one, okay, so here we go. Right, so we have a low sampling rate, right? Well, also a low bit depth. Remember, they also call this the sampling resolution. Well, then we're going to get a large error. And if you want to be specific, what you'd call this the large quantization error. Right, then of course, if we have sort of like a medium, right, make it a bit higher again. So yeah, let's say we increase the sampling rate. Right, we also right, also increase the sampling resolution. Right, of course, well, then we're going to get less error. And then likewise, in the third one, of course, yeah, just increase them. Well, I guess increase them even more. And then yeah, of course, here we're going to get the least error, right, the most accurate signal. So yeah, I think hopefully that makes sense. Right, then if we look at channels, so, okay, 2 audio channels means there'll be a separate recording for each speaker. And when we say speaker, well, we're talking about left and right. Each speaker or each headphone. Right, therefore, we would need to multiply we need to multiply our answer by 2, if we're trying to calculate the file size. Now, if the exam, if the exam question mentions there's 2 channels, right, well, yeah, then of course we multiply by 2. However, if they don't mention the channels, well, then you can just assume it's going to be mono. And mono just means 1 channel. Now, to be honest, I would say probably 75%, maybe even 90% they're not going to mention. So yeah, 90% of questions it's just going to be 1 channel. But yeah, of course, look out, right, if they do mention 2 channels. I guess, even more, right, could be 4. So just, if we have a look at this then, we can see in the second picture. Of course, okay, here it is. So of course, I guess, right, this is going to be the setting that we save the audio with. So if we then look at the second picture, well, we can actually see the left and right waveforms are actually different. Because if we look at this one, well, yeah, we don't really have that peak here. Likewise, we see this, where it's kind of like a fatter signal. And of course, there's various other differences you can see. Right, so we say, a single audio channel is called mono, and actually for the exam you don't need to know this, to be honest. But I think most people are probably familiar with this already, right? Yeah, I think a lot of people have heard of, mono sound. Probably people are even more familiar with stereo sounds, right? People have probably heard that term. That's going to be, again, sound with 2 channels, right? Both the left and the right. Right then, multi-channel or, surround sound. And again, people have probably heard of surround sound, when it comes to TVs, when it comes to, speakers. Right, so e.g., I guess, right, surround sound 7.1, this is just some specification. Right, this actually has 8 speakers and, they're arranged as shown. So, of course, this is the person in the middle, and then you got sort of, I guess, 3 speakers in front, right, 2 at the side, and then also, of course, 2 speakers from behind as well. So, yeah, kind of just kind of bombarding them with sound, basically. Alright, so if we try and calculate the file size again, right, so using these settings when exporting audio, right, and also assuming no compression, and I guess again, right, also assuming no file header. Now, if we just talk about that quickly, I think they wouldn't really mention this in the exam because, mostly for headers, they're talking about images. But of course, audio is also going to have a file header. So if you think about that, probably some of the information stored right in the audio header. Well, of course, 1 is just going to be the resolution. 2, you're probably, again, you're going to have the magic bytes, right, like we saw with the JPEG, where we said, every JPEG, I can't remember, was it like FF, maybe F8, and then something else, right? We say that, every JPEG, of that particular, version of JPEG, All right, like yeah, I guess well, all of them should start with this sequence of bytes. Yeah, just to kind of signify that it's an actual JPEG encoded file. So of course, right, yeah, we say, okay, well, okay, so the audio header, right, well, one is going to include some magic bytes to represent, MP3 or WAV or, yeah, some other file format. Right, there's probably also going to be the sampling resolution, because, again, you need to think, well, if you just have, a sequence of bits, and of course, yeah, well, that's going to go on and on. Like, if you're using, say, a sampling resolution of 4, well, then, of course, it means this is, the first sample, right, this is going to be the next sample, right, this is, the next sample. Whereas, of course, if you're using a sampling resolution of 32, well, then, of course, you're going to have, right, all 32 bits, which are going to be, well, yeah, of course, all 32, which are going to be the first sample. Likewise, well, of course, you also need to know the sampling rate, because, well, you need to calculate, at what, I get, okay, so you need to sort of calculate how quickly or, yeah, how fast to actually play the audio. And I guess, yeah, you also need to, of course, right, know the channels. Alright, so, yeah, I probably shouldn't have done that. Right, so if we just want to calculate the file size, then, so of course, well, here we're just going to multiply everything together. So we say, what the sampling rate, this is the number of samples per second, right? Therefore, if we multiply that by 32, because, well, of course, 32, right, that's going to be the size of each sample. Therefore, multiplying them together, that's going to tell us that's going to tell us the number of bits for 1 second of audio. But then if we think, well, then we've actually got 2 channels, so I guess we also have to multiply by 2. Right, then, yeah, okay, so that should be fine, right? Then, of course, we'll just have to multiply by 4. Well, I suppose it's going to be 4.5 in this case, right? Then, of course, we'll just multiply by 60 as well. Yeah, just to get, 60 seconds in a minute, and then, of course, 4.5 minutes. Then, if we multiply all of those together, I guess, then we can just divide. And again, we'll use a sensible unit. I think in this case, again, megabytes, mebibytes. So, of course, again, just do times 8. And then, again, right, 10 to the 6 for megabytes. And 2 to the 20 for mebibytes. Right, so if we do that, it's going to be 95.3 megabytes, right, or 90.8 mebibytes. Now, probably you might think, that's kind of huge, because, if you're familiar with just like a sort of 4 or 5 minute MP3, I feel usually maybe it's going to be maybe 10 or 15 megabytes. Yeah, probably quite small. Yeah, I don't know, maybe even smaller than that. Now, the reason for this is because, of course, right, this is not compressed. Now, in reality, MP3 compression can usually reduce by about 90%. So, yeah, okay, so when I say 90%, it's kind of going to 1/10 of its original size, effectively. So yeah, of course, that's why if we actually had compression, that would be, let's say, 9.53, yeah, which is probably more typical, right, in a real situation. Alright, so let's think then, what's going to be a problem if we sample at too low a frequency? And I would say for this one, just sort of pause the video, right, try and have a think of this, maybe draw a diagram, right, if it's helpful. So, the problem, of course, it's going to be that we couldn't accurately capture the waveform. And, let's think, right, what if we sampled at too high a frequency? So, in terms of accuracy, this is not going to cause a problem, but, there is going to be another problem. And hopefully you realize, okay, so here we say the waveform is actually going to be accurate, but, of course, right, the file size is just going to be unnecessarily large. Kind of like if we just have a simple image, we could save it with just, 256 colors, which, that's going to use 8 bits per pixel. Yeah, or in contrast, we could save it, let's say using 24 bits per pixel, and that's 16.7 million colors. Now, if we just have a simple image, honestly, it makes sense just to, save it with this. Right, so if we see a low sampling rate, also, of course, low sampling frequency. And in this case, they're sampling at, 3/4 the frequency of the cycle. So, of course, we see right here sampling at this rate, and then, of course, right, here is going to be the sort of full cycle. But yeah, of course, right here, they're only sampling at 3/4 of that. Right, likewise, yeah, the next one, right, the next one, the next one. Then, as you can see, if here we look at the reconstructed wave, of course, now rather than going sort of up and down like this, yeah, of course, we see it's then going to be reconstructed to here, and then obviously here. So what we're going to say is, of course, yeah, it's just going to miss out the peaks and troughs. And again, hopefully that makes sense, just by looking at, I guess, looking and comparing these two visually. Right, so this I guess not this process, but okay, let's say this problem. Right, this problem is called aliasing. And this is when the sound wave can't be reconstructed accurately due to sampling at too low of a frequency. And again, of course, we just see an example right in the picture. Right, so this is actually the extra thing I was going to talk about. Okay, well, this is called Nyquist theorem. Now, I remember when I was doing A-level, and actually, well, this was a different example, but for us, we had to do this. I think for Cambridge, they don't require it, although, to be honest, Cambridge also has a lot of extra stuff, which, my example didn't have. So for Nyquist theorem, well, this states that for a digital signal to be constructed accurately, then the sampling rate must be at least 2 times the maximum frequency. And when we say digital signal, right, I mean this is important because this is not only talking about audio, right? I mean this is talking about any any digital signal, right? I mean that could be sending Wi-Fi signals. This can be sending data over Ethernet. I mean just obviously kind of the mobile phone networks, right? Everything, 4G, 5G. Right, so for audio designed for humans to hear, then we can choose a sampling rate based on the frequency range that humans can hear. Now, maybe from, I don't know, maybe physics, biology, right, people should probably know what this is. So for humans, right, of course, 20 is going to be the lowest frequency, and then, 20,000 hertz, that's generally the highest frequency. Now, I mean, probably, most people can't actually hear that entire range, but, this would be, someone with good hearing, to be honest. And I suppose, I mean, probably young children, to be honest, since, of course, as you get older, right, of course, your hearing just kind of gets worse. So if we think then, well, what would be a good sampling rate, right, according to Nyquist? Because remember, he says, well, we should sample at least 2 times the maximum frequency. And of course, the maximum frequency here is 20,000. Right, therefore, if we choose double 20,000, so let's say 40,000, right, I mean, that should be reasonable. Now, in reality, 44,000 hertz is usually used, or 44.1 kilohertz. And I suppose there's a few reasons for this. I mean, one is kind of better just to kind of overcompensate, right, to overestimate, because maybe you have some people that have, super good hearing. Right, also there's a kind of more practical reason in that, just audio equipment is not perfect. There's going to be a little bit of distortion, it kind of can't accurately represent the sound exactly. So again, if you have these kind of extra frequencies, that's just gonna solve some of the problems with having this kind of imperfect cutoffs or imperfect filters. There's also another problem, and this is a sort of more mathematical problem, that if you sample at exactly 2 times the rate, then you could actually have a situation, if you're unlucky, where you actually take all of your samples at 0 amplitude. And I think no, okay, all right. So let's try to demonstrate that last one. So let's just draw this here, and I'll try to draw a sine wave, although it's probably not going to be too good. Alright, so let's say here then, and maybe I'll use a different color just to draw this. So let's say if we sample at exactly 2 times the frequency, then in theory you could get unlucky, and let's say here you take your first sample, which is 0. Alright, here you take your next sample, which is also 0. And of course, here you also take your next sample, which is also 0. Now, in that case, how do you know if, maybe first are we going up, right? Or, maybe alternatively, we're going down, right? So, I mean, basically, in this case, you just have to be guessing. And of course, I guess, of course, you could then incorrectly guess it's going this way. Whereas if in contrast, maybe let's use a different color. So if in contrast we sample at, I don't know, let's say 2.1, right? So just above the max, just above 2 times the maximum frequency. Well, then again, our first sample is going to be here, right? But then we say, our next sample is going to be just before. So this is going to be, just about positive, right? Our next sample is going to be what about here? So it's kind of just negative, right? Of course, our next sample is going to be about here. So of course, in this case, in this case, we can see, right, it's definitely going up, and then obviously going right up and down like that. So hopefully that makes sense why, it's obviously better to sample just above 2 times the maximum frequency. Right then, if we actually see this in a practical setting, then here we can see the effect. So here we can see the effect of increasing the number of samples taken. And I think here it actually shows us on this right chart. So it's kind of difficult to see. So and one, of course, right, it's saying here, we're going up to 10 times the frequency. So starting here at 2 times the frequency, and then so now it's getting to 5 times the frequency, and then of course when we get to the end, it's 10 times, and again, obviously you can see, right, this is just more accurately representing the sound. Hang on. Let's choose a different pen color since that yellow is super difficult to see. Again, right, so Fourier transforms, I mean, this is also not in A level, but I mean, if people do maths, right, well, I suppose maybe further maths, you might touch on this. But again, yeah, maybe it's interesting, right? So I mean, well, again, right, this is not only used in sound, right? This is used in all digital, all digital communication, right? Whether it's Wi-Fi, Ethernet, right, mobile networks, everything. So the important thing to note is that actually all wave types can be constructed just from sine waves. So if we look at some of the common wave types, well, of course, yeah, sine, obviously sine, right, the mathematical sine function. Well, then, of course, right, square, triangle, right, sawtooth. And maybe some people actually tried playing around with some, let's say DAWs, right, digital audio workstations. So if you've ever tried, I don't know, maybe something like FL Studio or Ableton, Cubase, maybe Logic, GarageBand. If you've tried any of those software, then you'll actually notice, right, for these synthesizers, they'll actually give you these bass waves. And then, of course, you can play them, right, you can hear the different sound they make. But if we actually look at them, for example, well, here the square wave, like the square wave, like in reality, I mean, this is like a mathematically kind of perfect square wave, right? In reality, a square wave is actually going to be represented like this, where if we actually look, right, there's obviously kind of mini sine waves, and then again we also get a kind of big sine wave up here. Likewise, so I suppose this is also a square wave, but just kind of more, I guess kind of like more similar to the square wave, kind of more accurately representing that. So right, this is a website that's quite interesting. I guess if you want to search this, right, of course, just find it. And well, this actually has a lot of interactive things you can do, right? So one of them is, well, basically you can just like draw some random scribble, as you see I've done here, and then it's going to tell you what, and then because what we say, remember that we say, well, all waves can be constructed from sine waves. So here it's actually going to tell us the sine waves that we need, right, in order to actually reconstruct this signal. And I think this website is also going to play it. Right, and then I think they also have other good ones, right? They have like a 3D version where you can just draw some scribble, then it's going to draw this like 3D model out of it. There's all kinds of like good animations and good interactive kind of demos on this site. Alright, so I think aliasing we've mentioned already, but let's just talk how this also relates to images. Okay, so for images wise, it's going to be where pixels are not small enough to represent the image accurately. So if we see, let's go next. So this is where images for games, videos, etc. will use something called anti-aliasing. And if people have played a lot of games, then if you notice, right, when you go in the graphics settings of games, right, there's often an option called anti-aliasing, which of course, you can either enable or disable, or turn on or off. And when we say anti-aliasing, well, effectively what that's going to do, it's just going to blur some of those edge pixels. Now you might actually think that, I guess, okay, so you might look at this and think, well, of course this is going to look worse. But when you think this is going to be small, and when you look at it from a distance, okay, actually, right, this one is actually going to look smoother. Whereas in contrast, this one, of course, even if we look at it from a distance, it's going to look kind of really janky like this. Whereas of course, with anti-aliasing, right, it's just going to look smoother because of the blur. Okay, so let's end then just with a recap of everything we've done. So we just wanted to find the following terms, right? Sample, sampling rate, or sampling frequency. Right, sampling resolution or bit depth, the amplitude, right, and also quantization. Right, and also quantization level. Alright, so what I say, well, pause the video and have a think. Right, once you've maybe thought or once you've written something down, right, then just resume and then let's see the answers. So for sample, we can say, well, this is going to be a measurement of the amplitude of the analog sound, right, at a specific time. And I suppose you can say, well, of course, right, this measurement is going to be converted into a digital signal. Of course, right, it's also going to be quantized, and well, of course, stored, on the digital device. Right, then if we look at the sampling rate or sampling frequency, well, this is just going to be what the number of samples that we take per second, or per unit time. Right, the sampling resolution or bit depth. Right, this is going to be the number of bits we use per sample. And of course, increasing this, well, again, it's going to be more accurate, but higher file size. Right, the amplitude, I mean, what that's just going to be, again, like if we want to say, simply, basically it's just the volume, but you can say, well, it's kind of like the distance from the origin, and I guess, that can be both, positive and negative. I think if you just say the volume, right, that should be fine. Right, quantization, so that was the process of taking the analog signal and then converting it into discrete levels. because, well, like we said, of course, okay, so of course, right, well, while an analog signal is going to be continuous like this, if we have digital, well, of course, we only have these discrete quantization levels, right? Therefore, we have to actually then, okay, so we've got to kind of like round our analog signal, right? Yeah, just to these discrete values, basically. And then if we look at the quantization levels, well, of course, that's just going to be, these levels here. So let's say quantization level, 0, 1, 2, 3. So I mean, hopefully they make sense. Right, then just a few more. So let's state the formula for calculating an audio track's file size. So again, these questions, right, well, of course, pause the video, have a go. Right, so if you thought of that, well, it's just going to be what the sampling rate multiplied by the duration. Okay, well, I suppose, maybe we can do this first, really. So if we do what the sampling rate times the resolution, well, this is going to tell us the number of bits for 1 second. Right, then if we multiply by the duration, well, of course, that's going to tell us what the number of bits, for the entire audio. And I suppose really, well, then, of course, we've got to multiply by the number of channels as well. Because if we think, well, of course, this is going to tell us what the, the number of bits for one channel. And to be honest, again, most exam questions, this is just going to be 1. So, of course, you can just ignore that, right, in most cases. Right, then just fill in the blanks. So sound in the real world is something, but has to be converted to something to be stored on a device such as a phone or computer. So hopefully people realize what the first one is just going to be analog, right, and then the next one is going to be digital. And then hopefully, again, people remember, well, we're just going to use an ADC to convert, right, so what, an analog to digital converter. That's going to be the electronic component that's, of course, we're going to, quantize the signal, right, convert from an analog to a digital signal. Right, then explain what happens to the audio quality and file size when the sampling resolution and sampling rate frequency are increased. And well, of course, remember the sampling resolution. Sampling resolution, right? We can also call the bit depth. Now, I think this one, I've said 3 or 4 times already. But hopefully people remember that. Well, of course, right. Well, okay. So of course, right. If we increase either of them, what the file size is going to increase. Likewise, the quality increases. Now, you don't only want to say that. Okay, you actually want to explain why. So I suppose what we can say, the digital sample will be will more accurately represent the original analog wave, and this is due to having more quantization levels. So of course, it's going to have more quantization levels because, well, sampling resolution or bit depth is increased, right, and also a shorter duration between samples. That's because, well, the sampling rate or frequency have increased. Right. Okay. So I guess kind of right. Therefore the quantization error will be reduced. However, taking more samples, per unit time and using more bits to store each sample, well, of course, that's going to mean that the file size will increase. Alright, guys, so I think for this video, well, that's all I wanted to say. Hopefully, again, this has been useful. If you've got any questions, well, just ask in the comments, and hopefully see you again in the next video.